Agora é a apresentação do professor Juan Salamanca, da Universidade de Cali, Colômbia. O professor Juan Salamanca é professor de mídias interativas e consultor profissional desde 1995 nas áreas de branding, embalagem, desenvolvimento de produto, direção de arte e pesquisa em design. Lecionou durante anos programação de computadores para artistas e designers. Possui título de doutorado pelo IIT, Institute of Design, Chicago, dos Estados Unidos, mestrado em direção de design pela Domus Academy, da Itália, e pela Pontifícia Universidade Javeriana da Colômbia. Atua como professor e coordenador do Departamento de Design na Universidade SESI, na Colômbia, desde 2000, onde desenvolveu o currículo da primeira pós-graduação em mídias interativas no país. Atualmente conduz pesquisas em design na área de interação social em ambientes aumentados, de realidade aumentada, perdão. Paralelamente ao seu trabalho de consultoria para empresas. As perguntas que vocês têm para o professor, que a gente sabe, vocês podem guardá-las, tá? A gente vai fazer um grande debate no final das apresentações. Façam mesmo com relação aos questionamentos para o professor Juan Salamanca. Então vamos agradecer a presença também do professor Juan Salamanca com uma grande salva de palmas.
Thank you, Mauricio. First, I would like to thank it's not easy. For the invitation. I would like to thank also ICD group for the amazing effort you're doing putting together this program. I'm learning a lot from your experience. Thank you, Mauricio, for the invitation and all the supporters and organizations that are sponsoring the workshop. To begin with my presentation, I would like to give a quick introduction of where I'm coming from. As Mauricio said, I'm coming from Colombia, and this is the campus, the university I work at. This Universidad de ICD is located in the southwest part of the country. It's a private university. It has about 12,000 students between undergrad and graduate students. And we have a design and engineering school. The design programs are located within the engineering school. And we have two programs in product design, and one program in product design, and the other one interactive media. And as Mauricio mentioned, this the first interactive media program in Colombia. And so it's a nice combination of fields, product design and interactive media, because it's a lot of new developments are happening in between. It's a space of tangible stuff and computational stuff. And so I work specifically in that area in between. My background is in product design. I study product design, teach product design. I don't teach product design anymore, but I used to teach design for product design students. Nonetheless, this is a combination of fields, and so in the university we had the support of local organizations. As I said before, it's a private university, and the support of local companies are big sponsors of the university. And so today I'm going to talk about smart artifacts and how they may support social cooperation. My research interest is specifically in in products and in how this computational artifacts may support social collaboration. And we are looking at that from the product perspective, but there are also many other applications in software, and I guess everyone is familiar to the concept of social networks. It's a way of supporting social collaboration. But I'm looking at how tangible products may support social collaboration. So that's my topic is going to be on that area and how these new ideas of products may support that part of the society. It's important to define here that there are different concepts of how to define a social society and how to define the human being and how to define a community. So, if any of you are from the social sciences, may have a different point of view from what I'm going to present here. Because from traditional social sciences, society is something that is the result of norms and institutions that are consolidated over time. But the point of view I'm going to bring here comes from a different perspective that is also acceptable in some social sciences, which is that society is emerging from the interaction of individuals. So it's single units, single agents, single persons interacting with each other, and as the interaction happens, society is constituted because there are emerging new rules, ways of behaving, or standardized behaviors. So it's not something that is imposed like education or gender or ethnicity. Well, ethnicity is not imposed, but not even gender, but it's something like macro ways of understanding society and organizing society. This is from the bottom-up perspective. It's more like looking at single individuals interacting with each other. And that's a conceptual framework that within I'm going to present my concepts. So we have on the screen this picture of this girl interacting with this doll, which is not a novel idea. This idea of building dolls is something that had happened traditionally with kids playing with this kind of devices. The interesting part here is that the doll talks to the girl. Well, that's probably not so new. We have seen dolls talking to kids for a long time. But the novelty part of this product, this toy, is that the toy is connected to a supercomputer. And the supercomputer is giving answers to what the kid is asking to the dinosaur. But it's not only that it's giving any answer, but it's a very smart answer to what it's asking, to what the kid is asking. So this device is connected to Watson. I don't know if you know what Watson is. If any of you probably have seen Jeopardy. It's a TV show. They invite very smart people and they ask very sophisticated, complicated questions, and these guys are competing for a big prize, giving best answers to those questions. Well, very difficult questions. This is something similar to Who Wants to Be a Millionaire, but the questions are even harder than those in the TV show. And IBM built this supercomputer to take part in that competition until he finally won the competition against the best players ever in that Jeopardy game. So this supercomputer is really capable of processing a lot of human knowledge. I'm looking for the best answer to some questions, or if its aspect if question are asked in a specific way. Let's say that the computer has all Wikipedia and also other encyclopedias inside and is capable of looking for the right answer in very short time and give the answer faster than any human. So this toy is connected to that computer, and whatever the kid asks to the computer, to the dinosaur, he's going to get an answer. So what we see here is that there is a toy or a physical component that is connected or extended to some sensors or actuators. In this case are microphones, microcontrollers, and speakers. And but there are many other ways of connecting and sensing devices and actuators to the tangible products. And what they do is amplify the value and capabilities of a regular product. As they amplify the capabilities, these smart components are enabling new functions to those products. So to me, that's a very interesting part from the industrial design point of view. I was trained in a very traditional way of designing products and yes, products. But at the moment I was studying industrial design, I had no idea that this was possible. Since 2000, the emergence of Arduino and microcontrollers that you can play with without having all the burden of learning electronics, but just basic knowledge of how to connect some components. Designers were able to bring those ideas into products, but that creates a new field of space of questioning of what design is, how to design those products. So when we design a product like this, well, one important part is how does it look, how it's going to be manufactured, how it's going to be packed, distributed, self-promoted. Many design fields involved in that part. But what is going on between this, and even more important, between the device and the kid, is still a field of exploration. And I find that very interesting and it elicits lots of curiosity how to frame design in a way that I should think, how a product designer gets involved in the development of this kind of products. So that, and continuing with this circle, well, it's not only about connecting things to these products, because that's, let's say, the first step. But it's about thinking that these components are going to be connected to other products and services. So it's not only thinking that's a single goal or a single product in your interaction with a single user, but it's probably many users connected through many products interacting together. And that's another space for exploration from the design point of view. So let's say the first extensions that you can see in smart products is how these devices talk to me just by giving me alerts or notifications. And it's something that we see regularly in electronics. Give me a sign that it's operating properly, or the battery is low, or the memory capacity is getting full. Those kind of signals that I'm getting from the device. And you can see that it applicated in many other products that are not necessarily using memory or many electronics are signaling this kind of alerts and notifications. But that's the basic way of thinking these kind of smart products. Controlling is another way of having an extended functionality, and it is how these devices are personalizing the user experience, so they change according to what I do, what I like, or my preferences. Another layer is how they perform better for me. So they use data that they are collecting as they operate, and they customize the way they operate in order to give a better performance to me. So let's say that our machines are constantly learning from what I do, from the way I operate. And finally, they coordinate with others and adaptively behave for me. And when we see projects like smart cities, it's basically working at this macro level. It's a traffic system coordinated with smart vehicles and traffic light systems and smart speed signs. And all of those ecosystems of elements are coordinated in order to enable the better operation of the whole city. It's a macro system, completely. It's a huge system with many different platforms acting together. So one example of how these products get extended is this basketball ball. And well, it's hard to think before you see this image, how can you innovate in this sport? Well, we have seen innovations in the garment, maybe smart clothes that makes the activity more, let's say, keep the temperature of the body, or smart shoes that collect some data from steps or activity that I run on the field. But thinking of how this work could be extended in functionality, well, this is an interesting idea. Some smart sensors inserted in the ball, and what is interesting is not the ball itself, but it's going on in the device, the smart devices. Just an extension of the ball and an extension of functionality, to the point that coaches are very concerned about what they're going to do, because all the training is happening on the smartphones. So this is like probably a complement or a tool that may facilitate or extend the functionality, the way coaches coach professional sport people. For this company, this is just one product. What is important really for the company is how to track this information. And there are extensions of, they are not only selling this, and they are selling the data to the customers in order to improve their performance. But this technology is not only applicable here, but it's applicable in any other sports, like golf, or soccer, or tennis, or, well, you can figure out, you can apply this anywhere else. So, these are examples of smart products, and just to give you an idea of what are the potentialities here. But the designer, it needs to think on not only the tangibility of the product, but also the potential extensions now. And I think that's the new field that interactive media and interaction design is really concerned about. When we think of product design and interactive media, we are thinking of all those extensions, all those potential applications. But as I said before, my interest is in social interaction and how these smart devices may enable new forms of collaboration or facilitate traditional forms of collaboration. So we see, for instance, this is an example of how single individuals interact together and they create something that is a system that is larger than the individuals themselves, which is a market. A market is basically an interaction of people who wants to sell, people who wants to buy, and the result is a price. The price depends on how much do I want to buy and how many people want to buy. Sorry, how much do I want to sell and how many people want to buy by offer. And that number, the index price, it's a measure of that interaction. But when we think of this from the, let's say, interactionist point of view, we have a simple model that economists and some biologists and sociologists define in terms of game theory. And when I say game theory, I'm not talking about video games, I'm talking about economics and how interaction of people is modeled in economy, economics, and biology, and different social fields. So the idea of game theory is that every single individual is pursuing its own goal and is trying to maximize its benefits as in the market. And when I interact with someone, I interact with the idea that I'm going to maximize my goals. But the other person is also trying to maximize his goals. So we may get into a conflict. And those conflicts are solved in the settlement of agreements between individuals. So I'm looking for devices that may help people to settle those kind of conflicts. And we see these kind of situations in everyday life, in everyday interaction. This is a situation in which many individuals are trying to reach their own goals. They are going to different destinations, but they manage to coordinate. And they manage to coordinate because in the negotiation of trajectories, they follow some rules. Because otherwise, they may not having this kind of mess. And nonetheless, there are clear rules on traffic. This is quite often. It happens regularly, constantly, everywhere in the world. So, imagine now that Google smart cards are going to come into this legislation passes, as it's being passed, for instance, in California. And I think it's going to be extended in the next 10 to 20 years to some other cities. Well, how these smart cars are going to mingle in these kind of scenarios? Are they going to be capable to solve the situation, or definitely smart cars are not going to have this kind of mess? Well, in my point of view, we are dealing with a hybrid system. Smart devices plus smart people all together trying to maximize their own goals. And that's a big, complex challenge. And my research is basically on how, if I take this device and I try to design this device in order to facilitate the cooperation with other devices like this, well, how can we coordinate those elements? In my research, I have studied interaction like this, interactions in the traffic system, and basically this kind of mess, I define that I define this as a kind of social viscosity. It's social viscosity in the sense that everyone is trying to flow, and as I try to flow, I obstruct or get into the flow of someone else. And so the flow gets reduced or slowed down. And that slowdown, I define it as the reduction of flow. It's called the higher the viscosity, the slower the flow. So that term, I'm going to use the term social viscosity to describe when things flow. They have a low viscosity. When things are very slow, they have a high viscosity. Or social systems have a high viscosity. Well, I already talked about game theory. And my case study right now is the design of the smart bicycles. Thinking of a bicycle as a way of transportation that it's going to have it's having lots of traction lately. And I would like to study how to design smart bicycles that facilitate cooperation between cyclists. This is a render from Foster Associates in London, and they are projecting that London could have this kind of highways that's specifically dedicated for cyclists. That would mean that many people would move on bicycles, similarly to how it's happening in Copenhagen or other Scandinavian countries, or the Netherlands also, where you see lots of cyclists and sometimes traffic jams of cyclists. Well, in my city, we have 400,000 daily rides by bicycle. We didn't have a good infrastructure to support bicycle riders, but we have lots of bicycle riders. Almost 12% of city community use bicycle, and we live in a city of about 2.3 million people, similar in size to Porto Alegre. It's a big number, and it's a lot of bicycles, but they don't have the right infrastructure. If you picture this scenario, it would be a different scenario for cyclists, and perhaps they will extend the number of users. So this is a situation I like to introduce just to depict the kind of challenge I'm working on. Imagine that all these bicycles are trying to pass through this narrow pass, and so what's the best way to solve this traffic jam? But having the less impact on social viscosity. So keeping the less viscosity as possible. And this, I'm going to call this a convergence zone. So this is the moment when many people get together, but when you get to the traffic jam, it's already too late. Yeah, you have to make a decision before. But the problem is that you don't have enough information before you get to the zone of convergence. Once you're already in the traffic jam, you are screwed up. You have no way out. You have to wait until you pass the congestion. But if you manage to have previous information, probably you have made better decisions, and you can find a different route. That's the way Waze gives you the solution. It's collecting data from many other people in the city. It's showing you congestion areas, and it's giving you information that, okay, it's up to you to change your road or continue on your road. Well, I have a different approach. I'm having this idea that there's a regulation zone. If I get information before I get to the traffic jam, I can change my behavior. But my behavior is not leave road and go somewhere else. It's to have the most adequate speed, so I could slow down and keep the flow, instead of getting all together to jam and block the flow, prevent the flow. So I need information before I get here, because once I get here, I already influencing negatively viscosity. I need to keep the viscosity low if I get information behind before. So there are three challenges to do that. First, we need an interface between the cyclist and the bicycle. And that's a, let's say, further design challenge. And an interactive design challenge also. Second, we need to communicate all these bicycles and get information from all of them in a network. And then we need to coordinate all of these bicycles somehow. So I'm going to talk about all these three challenges. This is an experiment. One part is the communication between bicycles. I'm collaborating with the Universidad de Chile and the Department of Engineering in the communication between the bicycles. We're using some technologies that are already in the market, but this one important challenge when we think about bicycles is that we can think of a network that has or a device that spreads signal to all the bicycles, but it may happen that this last one stays far away from the one who is sending the signal. So we need to replicate the signal from one to the next to the next to the next. And the same happens in the other way around. If this one is sending the signal to the first one, we need to propagate the signal according to the configuration of the network. But these networks are changing constantly, very dynamic, and that's a technical challenge. The one who is in front sometimes is the back, the one who is in the back sometimes the middle, and the one who is in the middle sometimes stops and just get to the destination. So it's a dynamic network, and that is a complex network configuration. We're using simple technology like XPs, this is an Arduino, and this is a GPS, and all these devices are signaling. And we have managed to develop a configuration in which, with very low power, many bicycles will get information from the whole network. Power is an important consideration here. It's not to consume all the batteries, just signaling data. We can use very high antennas that have consumed lots of power, but that's gonna, it doesn't make sense. We develop a mechanism that spreads the signals, propagates the signal in a very efficient way. So we're using simple and low consuming batteries equipment. The other challenge is platoon coordination. And so how am I going to keep the distance between the bicycles? And well, this is a well-known problem and it's already solved. So we're just borrowing solutions from the automotive industry. Google Car, for instance, and Volvo and BMW, they have already solutions for this. Where they have developed our basic algorithms so that you can automating out vehicles can just get into a platoon, and there is a leader, and they adapt themselves and coordinate themselves, just following some algorithms. So we're borrowing that, and we're bringing those algorithms to the coordination of bicycles, just to guarantee that between bicycles and you keep the same distance, and as the leader changes, all the other get a change according to what where we want in the system. What we define is basically a distance between one and the other, and they coordinate according to one leader. Well, just some experiments, just tell you, I want to introduce this way of doing research, which is somehow novel. I don't know if you use agent-based modeling, techniques of modeling to simulate social behavior. One of the important challenges when we think of social technical systems is that I can do ergonomic studies with one bicycle to one person. When we are thinking of a whole system, more than one person, more than one bicycle, well, we can do experiments in the lab up to 5, 6, 7, 8 people. But we're dealing with large complex systems, and we cannot work those experiments on the lab. So we need to came out with a technique that allows us to figure out what would happen if I have 50 or 100 bicycles running together. So this is a technique called agent-based modeling. It's defining a single agent, creating a population in the computer, and doing some experiments on what would happen if I change some specific attributes of my design. And what I'm showing here is one experiment that we have 4 bicycles, and this is bicycle number 1, number 2, number 3. And here we have an experiment where we wanted to keep the bicycles 2 meters one from the other. In this bicycle, in this case, 5 meters one from the other. And these are the results using the automated cruise control system, which is the algorithm that keeps that, and this is without that system. And so it's like a regular bicycle or a bicycle with the cruise control system. And this is the target. We want people to be at 2 meters, and with the cruise control system, it's very efficient. Bicycles stay at 2 meters, one from the other. Without that, the first one stays a little behind, almost 4 meters, and the next one stays 2 meters from the previous one. And similar results we are having with 5 meters. Well, but this is all simulated in the computer, and no humans are taking part of this experiment. So there are no actual cyclists there. I'm going to skip this one. One of the important challenges I told you is how to design the interface between the bicycle and the humans, or the cyclist. So just defining how to signal information to the cyclist is important, and cycling has lots of restrictions because the visual channel is constrained to, well, I have to pay attention to the road, and the audio channel is also not a good idea to use it unless you use some special techniques of bone sound communication. So it's not close to your ear, but transmitting sound through your bones into your skull. But we're using a different approach, which is sending signals through the hands, vibration signals. So we did a study of what are the most the contact points of the handlebar, and we define some areas that are most likely areas of contact, and so we run some experiments. What's the best signal to communicate information about speed with the rider, the bicycle rider? This is our idea. It's basically scratching your hand palm. So if you want you to go faster, it's going to scratch forward, and if you want you to speed down or slow down, it's going to scratch backwards. And we want to try if that idea is feasible and people really understand. Hey, go slower or speed up. So we designed this. This is our setup. It's basically a motor with some stimuli, and we tried 2 specific areas in the hand palm because well, if you are bicycle riders, we assume that when you touch the handlebar, you make the highest pressure. Well, that's the point where you are going to have the highest sensitivity. But probably it's the other way around. Probably you have the highest sensibility at the moment, okay, where you, at the point where you don't have that much pressure. Well, so we tried this. It happens that this is the lowest, the area where you have the lowest pressure, and this is the area where you have the highest pressure in your hand palm. And we tried that with some experiments. It happens that there's a significant difference. And the time response is almost the same in one part or the other. But the average number of errors, so people identify if the spinning wheel goes forward or backwards, it makes a difference. So it's much better to use to signal information in the areas of the hand palm where you have less pressure. Well, those are very technical findings about how to signal information. But one important part in the system is that humans are not as accurate as computers in the model, and thankfully, because we gather information that from the environment and, as Kay said, from the context that influence my action on the bicycle. So I already have some processing information that is going to give me or get information on how to act in the context. So I may speed up or slow down or not pay attention to the signal of the handlebar. So the results in our experiments are going to be more messy than we have from our simulations and the computer. Messy in the sense that probably a cyclist that is going to participate in the experiment is not going to pay attention to the signal, but is going to have to do something different. And so if that person is the second one in the row, it's going to influence the third, the fourth, the fifth. It's going to mess up the whole situation. But that's the nature of human beings. We are not as computers, so we have to take that into account in our system. And that is this error, the spacing error. So we're adapting the cruise control algorithm to insert that variable of human error. So we are expecting to come out with a new algorithm that may enable a good performance in the system, taking into account human error. And but that's it. That's part of the experiments we're working on right now. So this is an ongoing project, and I hope that by the end of the year we're going to have some results. And so just to conclude, that collective interaction is social viscosity, and the design of smart artifacts may influence the social viscosity, may reduce or increase the social viscosity, and that may affect the efficiency of the social system. And improving coordination is a collective experience. That is important. It's not a single individual making decisions, but it's not a group behavior. And this idea of groups interacting is happening every day of our lives. We're in that situation of cooperating and collaborating with others. And well, this idea of designing products that may support that collaboration is something that I find really interesting, exciting, and of course challenging. That's it. Thank you.